Hey folks, in this video we're going to start to look at the beginnings of graphs of polynomial functions. And the first note I have about polynomial functions and their graphs, we're going to say polynomial functions, their graphs are smooth, no sharp turns in them, there are going to be no breaks in them. I like to say that they're, quote, well-behaved. They're very friendly, smooth, no breaks. They're well-behaved graphs. I'd also like you to know a polynomial function just by looking at a function, that you know it's a polynomial function. And I could write down a big, long, ugly-looking definition of what a polynomial function is. I'm going to give you more of a working definition of a polynomial function. For a polynomial function, any variable you see, the exponent is going to be a positive integer. So there'll be no fractional exponents. They're going to be positive integers. You're not going to have a variable in the denominator of a fraction either. That's not a polynomial function. So here's an example of a polynomial function. F of x equals 4x cubed minus 7x squared plus 2x minus 3. See, that's an example of a polynomial function. Look at my variables x. The exponents are positive integers. I don't have any variable living in the denominator of a fraction. That's what makes this a polynomial function. So I don't see any radicals either. That's not polynomial. These are a couple of important items I need you to be able to determine for any polynomial function. Item 1 is the degree of the polynomial. Quite simply, the degree is the largest exponent that you see. So for this polynomial function, the largest exponent I see on a variable, is 3, right here. So the degree of this polynomial function is 3. The other thing that I need you to be able to determine for every polynomial function, besides the degree, the other thing is the leading coefficient. So let me write that down, the leading coefficient. All right, quite simply, the leading coefficient is the coefficient. Remember, coefficient's a fancy name for number. The leading coefficient is the coefficient that's with the term that is giving you the degree. So this is the term that's telling me the degree of the polynomial, the degree 3. The coefficient here is a 4. That's the leading coefficient. So the leading coefficient is 4. Let's look at another quick example of a polynomial function. Here's a polynomial function. I'll call it g of x is a 4 plus a 2x minus 7x cubed plus 8x to the 4th. Well, that's a polynomial function. I don't see any radicals. I don't see any variables in the denominator of a fraction. All my variables, the exponents, are positive integers, so it's a polynomial function. So now I need to determine the degree. Well, the degree, I'm looking for the largest exponent on the variable. Boom. The degree is 4. So the largest exponent's 4. The degree is 4. The leading coefficient. Remember, the leading coefficient is the coefficient that's with the term that is telling us the degree. This is the term telling us the degree is 4. The coefficient of that term is 8. So the leading coefficient is 8. This polynomial is actually written in what's called a non-descending order. At any time you can have your polynomial written in what's called a descending order. Now, descending order just means the terms go from largest exponent down to smallest exponent. Notice this polynomial, it's written in descending order. Exponents go 3, 2, 1. They progressively get smaller. If I rewrite this polynomial in descending order, I would have 8x to the fourth minus 7x cubed plus 2x plus 4. The degree is still 4, the leading coefficient is still 8, but I just wanted to point one quick little thing out to you. If your polynomial is written in descending order, the leading coefficient will be the first coefficient that you see. That's only true if your polynomial is written in descending order. Next up, I'm going to show you why I'm stressing here the importance of knowing the degree and the leading coefficient. It's something called the leading coefficient test. So when we come back, I'll be talking about the leading coefficient test. Alright folks, I'm going to take a quick look here at something that's called the leading coefficient test. For the leading coefficient test, it's going to tell us about the behavior of the graph of our polynomial function. It's going to tell us what's called the end behavior of the graph of the polynomial function. So I'm breaking it into two big categories. If your degree of your polynomial is even, or if the degree of the polynomial is odd. Let's do the even case first. So if your polynomial has an even degree, and if the leading coefficient is positive, so even degree, leading coefficient is positive, both ends are going to be shooting up. It's called the end behavior. Both ends are going up. Now, I don't necessarily know what's happening in here, but I do know both ends are going to be shooting up. So degree of the polynomial even, leading coefficient positive. The leading coefficient test tells us both ends shooting up. If the degree is even and the leading coefficient is negative, so you have an even degree polynomial and a negative leading coefficient, both ends of the graph are going to be shooting down. Again, I don't know what's happening in here. That's why I'm making it a dashed white line. Don't know what's happening. It's just that I know what the end behavior is. So even degree polynomials, positive leading coefficient, both ends shooting up. Negative leading coefficient, both ends are shooting down. Well, let's look at an odd degree polynomial. So if your polynomial has an odd degree and the leading coefficient is positive, this end is shooting down, that end is shooting up. And again, I don't know what's going on in here. It's just I know what the end behavior of the graph is. If your degree is odd, you have an odd degree polynomial, and the leading coefficient is negative. Well, then this end is going up and this end is going down. So again, I don't know what's going on in here. These are just little tips to help us eventually graph polynomial functions. The first thing, when I have a polynomial function, the first thing I look at is the degree and the leading coefficient. If my degree is even and the leading coefficient is positive, I know the end behavior of my graph. Both ends must be shooting up. If my degree is even and my leading coefficient is negative, I know the end behavior. I know both ends are shooting down. If my degree is odd and the leading coefficient is positive, I know this end is shooting down, that one's going up. Or if it's an odd degree polynomial and the leading coefficient is negative, I know that's going up and then this end is going down. So that's one of the first things I look at, and I'm going to erase the board here and I'm going to do a quick example. I'm going to put a couple of graphs up and we're just going to, just by looking at the graphs, determine the degree of the polynomial, whether it's even or odd, and what the leading coefficient must be, positive or negative. So come back for that example. Alright, hey folks, here's an example to make sure we understand the leading coefficient test and eventually what's going to be the power of the leading coefficient test. So in this example I have, I'm just giving you a graph. Can you tell me what the degree is, whether it's even or odd, and what the leading coefficient of the polynomial must be, positive or negative? So look at this graph. Both ends are shooting down. Both ends shooting down tells me that this polynomial has an even degree and a negative leading coefficient. It's just the leading coefficient test. Look at this graph. One end is shooting down, the other one is going up. That tells me it's an odd degree. And because this end is going down and that end is going up, I know it's a positive leading coefficient. And I hope that's making sense. I hope it's making sense on how we can use the power of this leading coefficient test. Next up, we're going to talk about zeros of polynomials, and then we're going to put this all together and actually graph a polynomial function. Hey folks, next up we're going to talk about zeros of a function. Zeros of a function, quite simply, zeros of a function are nothing more than where the function is equal to 0. Graphically, you could think zeros of a function happen to correspond with the x-intercepts for the graph of a function. And then there's this thing called multiplicity of a zero. Multiplicity is just a fancy way of saying how many times does the zero occur. You know, if that value of x that makes the function equal to 0, if it occurs 3 times, then you would say it has multiplicity of 3. For example, let's look at this polynomial function. F of x equals x squared plus 2x plus 1. If you're asked to find the zeros of this function, remember, you're trying to find where the function is equal to 0. That's what it means to find the zeros. So you're trying to find the values of x where the function equals 0. And as you see, we can factor this to x plus 1 times x plus 1. And then if you set each factor equal to 0 and solve, you would get x equals -1 and x equals -1. It's the same number. So for this function, we would say the 0 of this function, we would say the 0 is -1, and since it occurs 2 times, we would say it has multiplicity of 2, because it occurs 2 times. So that's what multiplicity is. Now here's kind of a cool, neat thing about multiplicity and how it relates to the graphs of polynomials. So this is just for multiplicity. If the multiplicity is even, so if you have a 0 that has even multiplicity, that tells us that the graph of the polynomial function just touches the x-axis at whatever the 0 is. Remember, zeros of a function are the same thing as x-intercepts. So if the multiplicity of a 0 is even, that means the graph is just going to touch the x-axis at that particular 0. Whereas if the multiplicity is odd, that tells us that the graph crosses the x-axis at that 0. Let's see how we can use all of this knowledge so far. The leading coefficient test, zeros, zeros being the same as x-intercepts, and multiplicity. Let's see if we can put that together to sketch the graph of a polynomial function. It's going to be the next example when we come back. Alright, here we are folks. We're going to graph this function. F of x equals x to the 4th minus 2x cubed minus 3x squared. It is a polynomial function. The first thing that I note is that it's an even degree, and the leading coefficient is a 1, that's a positive 1, even degree, positive leading coefficient, I know for the graph I must have both ends shooting up. I haven't done any work yet. I've just used the leading coefficient test. What I would do next I would try to find the zeros of the function. Remember, zeros of a function are where the function equals 0. So I take my function, set it equal to 0, and I'm going to try to solve this equation. Hey, look, there's a common factor here of x squared. So let's factor out the x squared. And that leaves me with an x squared minus a 2x minus 3. And if I keep factoring, this factors to, it looks like an x plus 1 times an x minus 3. So now I have it completely factored. And I set each factor equal to 0. X squared equals 0. X plus 1 equals 0. X minus 3 equals 0. Notice this gives me a 0 of x equals 3. And it has multiplicity of 1. It only occurs once. I'll make that little note here, multiplicity of 1. Here I get x is negative 1. It only occurs one time, so it has multiplicity of 1. And here I get the solution, or I get the 0 of x equals 0. But notice this has multiplicity of 2. It occurs 2 times. You know, x squared equals 0. That means x times x equals 0. So I would get x equals 0 and x equals 0. That's 2 times it occurs. So 0 is a multiplicity of 2, negative 1 is a multiplicity of 1, and 3 is a multiplicity of 1. I'm going to use that information to construct a very rough sketch of this graph. Let me get some scaling here. 1, 2, 3, 4. 1, 2, 3, 4. All right. Okay, so these zeros are going to correspond with x-intercepts. So I have an x-intercept at negative 1. I have an x-intercept at 0. And I have an x-intercept at 3. Those are my 3 zeros. Those will be the 3 x-intercepts. I know both ends have to be shooting up. One more time, even degree polynomial, positive leading coefficient, both ends are shooting up. And now I'm going to employ the power of multiplicity. At negative 1, it's an odd multiplicity, so the graph has to cross the x-axis. At 0, it's an even multiplicity, so the graph is just going to touch the x-axis. At 3, multiplicity is 1, so the graph's going to cross the x-axis. So I know both ends are shooting up. I'm going to get a graph that looks something like this. This end is shooting up. And I'm going to cross the x-axis there. And at some point I have to turn around and I have to come up and hit this x-intercept. That's 0, but notice multiplicity of 2, even multiplicity. I'm not going to cross the x-axis. I'm going to just touch the x-axis. Then I have to turn. I'm going to come down here. I don't know how far, but eventually I have to turn around to get to this x-intercept. And since 3 had an odd multiplicity, my graph will cross the x-axis, and then that end is shooting up. Both ends are shooting up. So that's a quick example of how I can use my knowledge of the degree of the polynomial, the leading coefficient, finding the zeros, and multiplicity of the zeros to construct a rough sketch of the graph. Now if you want to see how accurate my rough sketch is, why don't you put this in your calculator, put this into y1 in your calculator and graph it and see, I didn't do too bad. I'm going to do one more example, except this next example, I'm going to kind of turn things around on you. Show you what I mean when we come back. All right, folks, here's a graph. I've given you a graph. And my first question for you is, just by looking at the graph, can you find the zeros? Well, remember, zeros are going to be the same thing as x-intercepts. So let's look. It looks like I'm scaling the x-axis by ones. So it looks like there's a 0 at -4, -1, and 3. So those are the 3 zeros. Looks like the 3 x-intercepts. Let's make the following observation now. Let's not only find the zeros, but let's state the multiplicity. So look at the graph at x equals -4. Notice it is crossing the x-axis. If it's crossing the x-axis at -4, we have to have odd multiplicity. Look what's happening at -1. The graph's coming up. Oh, it's just touching the x-axis. And then it's coming back down, just touching. That is even multiplicity. Notice also here it's just touching. So at 3, the graph is just touching. Again, that's an even multiplicity. So just from the graph, I can see the zeros, and I know something about the multiplicity. Let me ask you this question. What's the leading coefficient? Also, what's the degree? Well, since one end is going up and one end is going down, it better be an odd degree polynomial. And since this end's going up and this end's going down, the leading coefficients should be negative. But what about, we know it has to be an odd degree polynomial. The next question is, what is the smallest degree? We know it has to be an odd number. So here's how easy it is to determine what the smallest degree is. Odd multiplicity. X equals -4 is an odd multiplicity. Think of positive integers. What's the smallest odd number? 1. X equals -1 is even multiplicity. What's the smallest integer that's even? Positive integer that's even. 2. And the same thing here, 2. So if this would be a degree of 1, it's the smallest odd number. If this has a degree of 2 and this has a degree of 2, simply add those up. I mean, this has a even multiplicity. The smallest even number is 2. Even multiplicity, 2. Odd multiplicity, 1. Add these numbers up. 2 plus 2 plus 1. 2 plus 2 plus 1 is 5. So the smallest degree this could be would be a degree of 5, which seems to make sense. This end's going up, this end's going down. 5 is an odd number. And if this 0 only occurred one time, this one occurred 2 times, and this one occurred 2 times, it seems like that would give me a degree of 5. So hopefully this is introduction to like polynomials and graphs of polynomials. Hopefully this is making sense. Make sure you're well versed with the leading coefficient test, zeros of polynomials, and the multiplicity of the zeros. That's it for this video. Thanks for watching.